Here's some solutions for problems from Chapter 13, the first problem set. A few things that we've worked up in class today, not today, sorry, I don't know when you're watching this, but over the last few days, say. The first relationship, which we really got experimentally, is that we have Newton's law of universal gravitation, which looks like this. And it depends on all the things that you would expect. It depends on the two masses of the objects, and it also depends on the distance between them. It is related, it's the inverse square relationship. This is one of many things in physics that follows an inverse square law. And that's our constant, the universal gravitational constant. And in case I didn't mention this in class, it's a number that's sort of annoying enough that you might want to save it in your calculator. I have mine saved as capital G, so when I type in alpha G in my calculator and it gives me capital G there, I hit enter, there it is. There's the gravitational constant. How do you do that? You type in the number, 6.673 times 10 to the negative 11th, and you hit the store button. It's right above your on button. Store, and then you just type in the letter you want to store it as. That's alpha G. And then it's stored as that number, or as that letter, rather. Now, just a word of warning, if you use programs on your calculator, including if you play games, any program that uses this variable, the letter G as a variable, it will overwrite this. So it's always a good idea, especially if you use programs in your calculator, before you use it, to just make sure, just type alpha G and hit enter and make sure it's there. Okay? Alrighty, let's get started. So the first couple of problems just use Newton's universal law of gravitation. Number one, a mass is split into two parts, m and big M minus. So we have some big M, and we're going to split it into two parts that we're going to call small m, and then the rest of it would have to be whatever the big M minus that, so that they would add up. When you add these up, you get m. And they would like to know what ratio of m, small m over big M, maximizes the magnitude of the gravitational force. Well, if these are the two masses, then the gravitational force would be equal to G times little m times m minus m, big M minus small m, over r squared. And this is constant, and they're saying at a fixed distance, so that's also constant as far as we're concerned here. So we have this expression here, and you could, if you wanted to, you could make, you could go ahead and distribute that. That's G over r squared times m minus m squared. And thinking about this like a calculus student, if we're trying to find the maximum of something, then we want to take the derivative and set it equal to 0, right? Now notice that the big M is a constant, right? The variable here, in this whole expression, the only variable is the small m, how much we're going to break off, and then the other part will be the big M constant minus the little m variable. So if I want to take the derivative of this and set it equal to 0, the derivative of this will be the constant G over r squared times, and then the derivative of, if that's the variable, that's like m times the variable, so the derivative of that would be big M minus 2m. And if I set that equal to 0, well, this is just a constant. That can't be equal to 0. This is the part that would have to be equal to 0. And I get that little m would have to be big M over 2. And therefore the ratio of little m over small m would be equal to little m is m over 2, and big M is just big M. That's equal to 1/2. What does that mean? it means that it would have to break into two equal-sized pieces, right? One piece would be sized m over 2, and if they both add up to m, well, then the other one would also. That kind of makes sense intuitively, I think, that if you want to maximize the gravitational force, you'd break it into two equal pieces. That's what that looks like. Number 3. What must the separation be between a 5.2 kilogram particle, so again using Newton's universal law of gravitation, and here we're solving for separation. What would the separation have to be? Right? So I'm solving for r. So if I do a little cross multiplying here, I get r squared is equal to g m1 m2 over gravitational force. And if I want to solve for r, I take the square root of that. And I think they gave me all of the things here. So g times one mass, 5.2 kilograms. The other mass is 2.4 kilograms over, they want us to have a gravitational force of 2.3 times 10 to the negative 12th newtons. I just have to crank that out of the calculator. So I get the square root of g times 5.2 times 2.4 over 2.3 e negative 12. If you choose to, instead of using the e exponent entry here on your calculator, and you do times 10 to the whatever, then you'd have to have that in parentheses on the bottom. Just be careful about that. So that would be a separation of 19 meters. And I'm looking at the answer in the book, and it does not agree with that. So I'm going to see, what did I do wrong? Let's see. Make sure I solve that equation right. Gmm over r squared. I move that over here. Put my gravitational force there. Gmm over gravitational force. I don't see anything that I did wrong. Make sure my g's in there right. It is. Interesting. And I did take the square root. Well, and we'll go over that again. Maybe you've already spotted the error, and this is extremely annoying to you. I really don't see anything. Let's just try it again. Let me run it through again. So the square root of g times m, those are my two masses, divided by the gravitational force, which is 2.3 times 10 to the negative 12th. Well, I'll let you figure that out. The answer that the back of the book has is 8/10 of a meter. Oh, no. Just kidding. I'm looking at the wrong problem. It is 19 meters. Wow, that was probably super annoying, even if you had already checked your answer. So, sorry, I was looking at number 5. So we did it right. Okay. Now, before I go on to these other problems, 43, 45, and 47, those problems really use Kepler's third law. And Kepler's third law is not something you can just drop on an assessment. That's something you have to know how to derive. And I think that's an extremely important thing to understand. And I'm going to go ahead and go through it again here before we start using it. And on the way to deriving it, we also get the formula for the velocity of something in a circular orbit. So where do we start? We start with the idea that we know that if something is in orbit, the only force acting on it is the universal gravitational force. And if it's in a circular orbit, that must be the thing that provides the centripetal force. So I know that this is G m over r squared. The convention here, sometimes you can subscript these, you could do 1 and 2 if you want, but usually when it's in orbit you use a big M for the thing in the middle and a small m for the thing that's orbiting. And then on this side I have mv squared over r, that's centripetal force. And pause here to just think about, should this be the big M or the small m? This centripetal force is the force acting on the thing that's going in the circle. The thing that's going in the circle is the small m, right? That's the orbiting body, not the big thing in the middle, the small m on the outside. And then there's some things that can cancel out here. The small m's cancel, one of the r's cancels, and I end up with v squared is equal to gm over r, or velocity of something in a circular orbit is equal to the square root of gm over r. Again, you need to know how to derive that. I mean, that's it, to derive it. It's just one equation and a little bit of canceling and a square root. You can't just drop that out of nowhere, but it's certainly a very good thing to know. Okay, so going from here, I also know the velocity of something that's moving in a circle is equal to the circumference of that circle divided by the period. And if I set these two things, those two v's, those are two v's that must be equal to each other for a circular orbit, I get 2 pi r over t is equal to the square root of gm over r. And this is the equation. When I square both sides and move things around, I'll skip the little bit of algebra there. That's Kepler's third law. Sometimes called Kepler's law of periods. But that's how you derive it, right? And this, notice, is a constant. Right? I'll just forewarn you that at some point you might see a free response question where you're given some t values and r values, and it says, what could you graph to get a straight line that would yield the mass of the central object? So the thing you would graph would be like, this is y and this is x. So you'd graph t squared versus r cubed, and t squared versus r cubed, that should give you a straight line. And the slope of that line would not be equal to mass, it would be equal to this. Right? This whole thing would be equal to the slope. This is sitting in the place where the slope is, right? Y equals mx. There's your slope. All right, anyway, now that we have that derived again, let's take it for a spin. Make sure I'm doing the right ones here. 43. All right, so first question, what linear speed must an Earth satellite have to be in a circular orbit at an altitude of 160 kilometers above the Earth's surface? Well, I know that the velocity of orbit has to be equal to gm over r. One of the tricks here is the r here is equal to the altitude plus the radius of the Earth. Right, if you think about that. The r in all of these equations is the distances between the centers of the objects. When we're talking about like the Earth and the Sun, the radii of those objects is so small compared to the distance. But when you have a satellite orbiting the Earth, that is not true at all. So here, from center to center, we want it at an altitude of 160 kilometers, which is 160,000 meters, plus the radius of the Earth, which is about, I'm not sure what our book gives, I think like 6.37 or 38 times 10 to the 6th. Geez, I should check that. I guess we'll see if we get the right answer here. Meters. So the r we need to use is the sum of those two. And that gives me 16 plus, 53, 6.53. You can check my work there, right? Because this is happening, this 1/6 is happening in these places here. You can do it with your calculator, of course. So that's my r. And then the mass of the Earth, oh, I'm trying to remember these things off the top of my head. I might have to look that up. I hope I'm not mixing those up either. No. Let's see, mass of the Earth. Well, if you haven't found this yet, there's an appendix in the back of your book, Appendix C. It's called Some Astronomical Data. And let's see. There it is. Mass of the Earth, 5.98 times 10 to the 24th. And they have, yep, they used this number, 6.37, so I remembered that. So the mass of the Earth is 5.98 times 10 to the 24th kilograms. Right? Near enough, 6 times 10 to the 24th. You'd be given these numbers, of course, if you needed them in some problem. The real important thing here is to realize that you have to do this sum. So the velocity, part A, of this orbit would have to be the square root of g times the mass of the Earth divided by the radius of the orbit, which is 6.53 times 10 to the 6th. And let's go ahead and calculate that. So g times 5.98 E24 divided by 6.53 E6. That's about 7,800 meters per second. There's our answer for that first part. Our book kept one more sig fig than that. We'll see if that affects other things. And then part B, they would like to know what's the period of revolution. The easiest way to do that, since I now know what the V is not from this equation, although you could use this to find the period. This is easier, because we already found the V, right? So 7,800 is equal to 2 pi times the radius of orbit. I guess all these other numbers have 3 sig figs. I probably should have kept 3 there, but sorry about that. Over the period. So by cross multiplying, I can switch those, which means that my t, my period, is equal to 2 pi times 6.53 times 10 to the 6th divided by 7,800. And I have a syntax error. What did I do? Oh, I have a rogue parentheses there. Didn't need that close there. Oh. Jeez. Making this look harder than it is, huh? Second entry. Nope, not going to give it to me there. So let's hit enter and let's hit go to and see if there we go. Haha. So by my only 2 sig figs, I should call that 5300. So the period is 5300. This is the period, and I'm all in SI units, so that'd be seconds. 5300 seconds. And they changed that to minutes because that's a pretty weird way to measure time. So to change that to minutes, if you wanted to do that, you divide by 60 and get about 87, 88 minutes to 2 sig figs. That'd be 88 minutes. And they have, what, 87 and a half minutes. So there you go. And that's about right. I think the International Space Station goes around every hour and a half. So that must be about the altitude that it's at. Number 45. The Martian satellite Phobos travels in an approximately circular orbit of radius 9.4 times 10 to the 6th meters. Now they're telling us the orbital radius here. So that means I don't need to worry about the radii of the planet or anything like that. They're saying this is the orbital radius. They didn't say this is the altitude, right? That's very important to understand and read carefully and make sure your brain is switched on. And it has a period of 7 hours and 39 minutes. That's not 7.39 hours. You cannot do that. You should understand why. So here, I'm going to change this to seconds. I know that there are 3,600 seconds in an hour, right? That's 7 hours. Plus, there's 60 seconds in each one of these minutes. So that's about that many seconds. And they want us to use this data to calculate the mass of Mars. Well, I've got radius and I've got period. And I know that this is Kepler's third law. So I'm going to take this and I'm going to solve for m. I'm going to move the m up here and the t squared down here. So that gives me that the mass of Mars is going to be equal to 4 pi squared times the radius cubed over g times t squared. Right? Let's just do a little bit of basic algebra there to rearrange that. Alright, so let's give that a shot. 4 pi squared times the radius, 0.4 times 10 to the, times 10 to the 6th cubed divided by, and I'm going to put this in parentheses down here, g times the period in seconds, is 27,500 squared. I know some of you like to go through and you like to do part of it and then hit enter and then hit enter. It really, I think, there's a benefit to having the whole thing in there at one time so you can really see the whole calculation. I would encourage you to do that. So it looks like the mass of Mars is approximately 6.5 times 10 to the 23 kilograms. And we can check in the back and see how close that is. Flip back to that appendix and see what it says about the mass of Mars. Mars doesn't have a lot of moons, not enough, didn't make it into our lab exercise. So Mars, the mass, gives it in terms of the Earth mass. So it's 0.107 times the Earth's mass. And the Earth's mass we just did was 5.98 times 10 to the 24th, and they give it so it's 0.107 times the mass of the Earth. It's about 11% of the mass of the Earth, 0.107. And pretty close. It's about 6.4 times 10 to the 23rd. Why might we have been a little off? Well, we rounded some here and there, and in fact, the orbit's not quite circular. It's elliptical, so that does change things a little bit too, but that's a very good estimate. All right, one more problem. Number 47, not 27, right? We have here the Sun, which is a distance of 2.2 times 10 to the 20th meters away from the galactic center. It revolves around that center once every 2.5 times 10 to the 8th years. That is 1/4 billion years, 250 million years it takes for the Sun to go all the way around in our galaxy one time. That's kind of amazing to think about. So the age of our Sun, that's not something I know off the top of my head. But assuming our Sun is not too old, let's say our Sun is about maybe, 8 billion years old. You could Google that real quick. But if it was 8 billion years old, that means since the formation of our Milky Way Galaxy, it's only gone around really just a few handfuls of times. It goes around 4 times every billion years, so about 32 times or so that it's gone around. So let's do age of the Sun. I mean, you look these things up, right? Aren't you curious? Oh my goodness, I overestimated there. It's only about 4.5 billion years old, about 4.57 billion years old. So, and let's do also age of Milky Way Galaxy. Milky Way Galaxy. Our Milky Way Galaxy, on the other hand, is about 13.2 billion years old. So, of course, galaxies are the birthplaces of stars. So, our star is fairly young. So there's some stuff to think about anyway. Pretty profound, I think, when you think about our little planet whizzing around our Sun once a year. So, anyway. Assuming each star in the galaxy has a mass about equal to the Sun, and the mass of the Sun is about 2 times 10 to the 30th kilograms. And assuming that the stars are distributed uniformly in a sphere, which is not true, by the way, you know that they're in sort of a flat, more like a disk about the galactic center, and the Sun is at the edge of that sphere, estimate the number of stars. Now, why are they asking us to estimate it like this? Well, I think at this point we probably would have talked about in class. So if this is our Sun out here, and this is the whole Milky Way populated by many, many, many stars, the Sun responds to the presence of all these stars as if this was a planet. It doesn't make any difference if this is like the stars are all scattered all over the place or every single one of them is concentrated in a giant lump in the middle. It does not make any difference to the Sun. So, in other words, if the entire Earth were compressed down to a point, and you and I were at the same location that we are now, we would feel the same gravitational pull. Of course, there'd be a lot of empty space underneath us, but if we had some way of remaining where we were, we would feel exactly the same gravitational pull. So the distribution of things doesn't matter, as long as it's uniformly distributed, and that's what they're suggesting. So what they're, I think, suggesting that we do here is consider that the whole Milky Way Galaxy is like that mass in the middle, right? So we have Kepler's third law, t squared is equal to 4 pi squared, or gm over r cubed. Now look, here I am just dropping that equation. You can drop it in the homework problems if you know it. I guarantee you that if it comes up on a free response question, you will have to derive it, right? And you know that that's pretty easy to do. We did that just a few minutes ago. Here I'm just going to drop it on you. And let's see what we need to do now. I guess I need to change this into seconds. So that's 2.5 times 10 to the 8th times 365 days times, I happen to remember that there's 86,400 seconds in a day, so that gives me about 7.88 times 10 to the 15th seconds. Right? And I think we're good to go now. Again, just like the last problem, I'd like to solve for the mass of the unit of the Milky Way Galaxy under these assumptions. So that would be 4 pi squared times r cubed over g times t squared. Just swapping the places of those cross multiplication. And that gives me 4 pi squared times r cubed. Your calculator recognizes the order of operations priority here is that that's one number, so it will cube the whole thing, not just cube the 20. Divided by, in parentheses on the bottom, g times the period 7.88 E15 squared. I think I got everything in there, right? And that gives me that the mass of the galaxy, and we're just approximating, so I'm just going to call that 1.0 times 10 to the 41 kilograms. Sorry, that's my exponent there. 41 times 10 to the 41 kilograms. And if that's the mass of the whole thing, and it's filled up with stars that have the same mass as our sun, then the number of stars is just the total mass divided by the mass of each star. I'll take that number here and divide by 1 times 10 to the 41. Oops, sorry, divide by the mass of the sun, which is 2 times 10 to the 30th. And that gives me about 5 times 10 to the 10th stars in the galaxy. That is about 50 billion stars by this way of approximating it. Now the assumptions here are not actually true, so we could also look up what do we think the number of stars in the Milky Way. And that's, in fact, it's more like 100 billion. This is 500 billion. So we got an estimate that was about 5 times too big, which is not a terrible estimate at all. Why are we off? Well, first of all, the stars are not uniformly distributed. There's more in the middle. It's not a uniform distribution. It's a disk, not a sphere, so we couldn't make that same assumption. And also, there's a big old black hole in the middle. You know what it's called? It's called Sagittarius A. And I know that because I'm a physics teacher, but I'm also Sagittarius. So I guess you'll have that. So those are some reasons why our approximation might not be perfect, but it's still pretty good, right? Only off by half an order of magnitude. So there you go. There's some universal gravitation. This stuff, these problems are fun. I think they're annoying because of all of the scientific notation, these very sort of unwieldy large numbers we have to deal with. But they're awfully fun in the, I think, humbling scale of the things that we're dealing with, the time scales and the masses and everything. It's just fun to think about this stuff and think about our tiny little place in the universe here, and that this is only one of many, 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 many galaxies. So there you go, just in case you were feeling all important or special or anything like that.